question to challenge the recorder?
We would like to challenge problem number 14, polygon rocket.
Number 14?
14, yes.
We would like to accept.
Okay, so number 14 is okay.
We would like to accept.
Yeah, please write down the representative to each of your team. Miracle, which one?
This one? This one, correct? Yes. Okay. All right. Now, second. Yeah, sure. So, you ready? No.
Yeah. Next two. Ready?
No.
Yeah.
Okay.
可以帮我坐到那边的桌子吗？不行，其实这边也可以。因为那边我怕太挤。
that pumping air into a plastic water bottle partially filled with water. Under certain conditions, the bottle is launched and flies into the air. Investigate the accelerations during liftoff depends on relevant parameters. Our key question raised after stating the question is the parameters that affect the acceleration of the rocket during liftoff, then to observe the motion during liftoff. This is a video. As you can see, the water launches into the air into a certain height. This is how I will go through our presentation from preliminary observation to theory to experiment setup to conclusion. In our preliminary observation, we discovered that when the pressure inside the bottle is greater than the external pressure, the water inside the bottle will be ejected under pressure and causes a force to the water, and the body will get the thrust and then accelerated and launches into the air. The launching process can be divided into two stages. The first stage is the water thrust, which we believe that the primary force propelling the water rocket to go upwards and accelerate. And then water rocket will go upwards, which is going into the second stage, double coast. This is our observed method. We use camera to capture slow motion video and then analyze the video. And this is the air pump, which we use to pump air into the rocket. This is the launch pad, which we use to ensure that the rocket is launching directly straight up, and this is the rocket. For our theory, this is a diagram of the water bottle rocket and forces that will affect it all. As the question stated, to calculate the acceleration in the z direction, we have to first determine the thrust of the rocket divided by the mass minus the air draft minus the gravity. And to determine this equation, we have to first figure out two variables, which is the exiting velocity of the rocket and the mass. With control value consisting in the interior rocket and the fixed share, we can get this equation, the second equation of the space of the compressed air in the rocket, which equals to the initial space of the compressed air plus the space created by the water exiting the rocket. And for the second variable, the mass, it is equal to mass of the shell plus mass of the air, which is negligible, and plus the mass of the water. The jet exhaust velocity is determined by the transformation of the energy caused by the pressurized air into kinetic energy, which is affected by the water jet. For inviscid, incompressible, and steady flow in the rocket, we figure out an energy equation of the Bernoulli's equation, which inviscid is met by the efficient nozzle design, and the incompressibility of the water, and the steady flow, which is not rigorously met, but the comparison of the time for unsteadiness versus the convection of the water shows that the process is quasi-steady. And to determine this, as I mentioned, the exiting velocity of the water, we have to first determine this variable, which is the pressure of the compressed air. And to determine the compressed air, we must have the knowledge of the expansion process, which is very fast compared to the time scale for heat transfer. Which the time for unsteadiness is much smaller than the time for heat transfer, which is approximately 10 seconds. We can combine the formula I showed earlier to calculate the value with the adiabatic expansion, which will result in this formula. And the first parameter we decided to use is the different initial water parameter. Both of the rockets exhibit a similar trend. The acceleration first increases and then decreases as the water volume changes. A larger initial injection of the water does not mean a bigger acceleration. If the initial water injection is not optimized and too much water is added, the water injected will act as a resistance because of the gravity affecting to the water, and then the acceleration will not reach its maximum. On the other hand, if the water is too little, the gravity it will not be able to generate momentum and enough thrust to reach its max acceleration. And second parameter sets is the different size of the rocket. As you can see, this is the data we use. We analyze this using the trackers. For the ideal condition of the acceleration, rocket will first reach its max acceleration before the max velocity, and then reaches to 0 during its max velocity, and reaches to negative when it reaches to its maximum height. So these four graphs all follows the trend of the acceleration in the ideal condition. But however, you can notice that there's a bit of oscillation happening to value due to the error of the tracker. For the 2,000 milliliter rocket, it also shows that it follows the trend of the acceleration in the ideal condition. And you can see that it also oscillates a little due to the error of the tracker. But what caused its oscillation is that the 500 milliliter water has more mass compared to the others, so which led to an instability in motion. The rocket wobbles more in the launching process. So if the rocket wobbles more, the tracker software may introduce tracking errors, causing the acceleration volume to oscillate more than it actually does. Okay. This is the linear time to max acceleration graph. The max acceleration always occurs during the water in the. The max acceleration always happens during the time for the water in the same gravity. This is our result. The orange line is the predicted value we use, and the blue line is our experiment data. As you can see, in both graphs, the predicted values are slightly higher than the real data, but the trend is similar, which it reaches a maximum acceleration in the intermediate value. The 2,000 milliliter water has a larger errors, possibly due to air drag and energy loss, which the model assumes that the ideal water ejection is deficient, while the actual ejection may involve energy loss. And the second is that larger rockets can sustain thrust for a longer duration, making them suitable for higher altitude flights. And the conclusion, the water volume, the optimal water volume is an intermediate volume, as I mentioned, around 10 to 15% of the total rocket volume, producing the maximum acceleration. As I mentioned before, too much water may increases the total mass, but may act as a resistance because of the gravity affecting the water, which will reduce the maximum acceleration. But too little water added will lead to insufficient thrust, resulting in low acceleration. The bottle size. Larger rockets can sustain thrust for a longer duration, and larger rockets oscillate more during the data analysis because of the error. As I mentioned, larger mass of the water will lead to the wobbling of the rocket, which will lead to the tracking error of the tracker. Thank you.
Component.
Okay, so I have a few questions for you. So first, did you add an error bar in your experiment?
No.
What do you think is the main factor of the error in your experiment?
Of our error. For the error, I think because of the tracking error I mentioned, this is actually the original data for the tracking, but as you can see, it oscillates like crazy. So we combine 3 frames of the video into, we combine 3 frames of the video.
No, I'm asking about the error. Where do you think the error comes from?
What? Sorry?
Where do you think the error comes from? What causes the error?
The tracking process
On the tracker.
in the tracker software.
So it's only the error is only in the tracker.
Yes.
Okay. So in the experiment, you change your barrel size, and did you control the mass, or so for different bottle size, you change the volume of the bottle? Is that what you're trying to say?
What I'm trying to say.
if you change the model size, so are you saying that your parameter is different volume of the volume of water?
The volume of the water is really the same between both experiments.
So change the volume of air in this experiment.
Also, so the volume of you mean the size of the bottle?
Yeah, so did you change the volume, because you changed the size of the bottle, did you change the volume of the air inside the bottle?
Air, yes.
And you change the mass of the rocket, also mass of the rocket.
I think it can be negligible.
Only you have 3 minutes. Very short. Okay, bonus, please take the floor.
Okay, this is a podium from me and D. Joker, and today we're going to discuss about problem 14 water rocket. And this is a broad statement. So the recorder's main focus on this problem is the parameters that affect the acceleration calculation problem, and also the motion period problem. And for their theory, they calculate the thrust, which is the force generated by the water. And they also consider the adiabatic expansion due to the short interval of time for heat loss. And for the setup, they use water rocket pump, launch pad, and camera. And they did only 2 different parameters. One is different initial water volume, and 2 is the size of the rocket. And we think that this isn't a very good parameter. And for the conclusion, they think that the water volume, the rocket, which is 2,000 milliliters of water, the water volume is going to have maximum acceleration. And they think that the acceleration trend is the same as history because it didn't explain where the error comes from. So these is the overall advantages and our suggestions for the recorder. first to have a clear graphical demonstration. But we suggest that they need more error correction and error explanation. And also they have inadequate parameter consideration, especially on changing the size of the model. And third, they didn't have sufficient data explanation. And these will be the points of discussion. So I would invite the reporter to discuss with you. Okay, so first, can you please turn to page 10. I'm sorry, page 11. Yeah, so here in your data, the data points are the experiment data field, right? So how can you know that it is a linear correlation between two of your experiment data? Why are you drawing those lines in your data?
Oh, this is actually not linear, but as I mentioned, it reaches an intermediate value.
Yeah. But yeah, so you don't know the value of your experiment data in the middle of 2 points, right? Like between the 2 points you did, you don't know the value of it because you didn't do the experiment for different water volume. Like for
Okay, so maybe I don't need to like connect the dots. That's what
yeah,
you're
because
trying to say?
you connect out, I think that you are trying to say that it's a linear.
Oh yeah,
correlation.
that may be misunderstood.
So you agree that you have to we cannot like
Yes.
connect it. Okay. And next, in your experiment data, where is your error bar?
Error bar?
Yeah, why didn't you add an error bar in your experiment?
We only did it once.
Where did you add your error bar? You said it once. Then
Yes, we did the experiment. But we didn't add the error bar.
So you only did the experiment one time,
Yes.
and then you put the dot into this graph.
Yes.
Then how do you know that your experiment is correct? How do you know this value is correct?
Because it matches this dV and how the acceleration is
Okay, then
distributed.
did you show the theory in this picture?
Not this picture. Oh yes. This is the volume we concluded in our theory, and this is the actual volume.
Yeah, okay, so you compare it to your series theoretical data. Then, so after comparison, then I can see that your experiment data and your series data they don't fit to each other. Like there's obvious deviation between your experiment and series data. Then how to explain it?
The energy loss, as I mentioned.
What energy loss?
Energy loss, like for instance, the water friction between the water and the bottle.
Only the friction between water bottle and water.
Maybe also we also consider the air drag in our data.
So think that the air drag force and the energy loss is your error.
Sorry, the air drag force is also considered in our
Okay, then can you please turn page 7? Yeah, so talking about the same thing, here you consider air drag force in your theory. And then you said that your experience data error comes from air drag force. So are you saying that your theory is wrong?
Okay, so I think there's a mistype in the presentation. I think the main source of our error comes from the energy loss, not the air drag. Because as you mentioned, we consider the air drag in our theory.
Yeah, but if you consider air drag in theory and then it still causes the obvious deviation in your experience data, then how can you show that your theory is correct or your experience is correct?
In the theory, we didn't consider energy loss between the water and the bottle. So maybe that's the source of the error.
Then did you try to calculate how much energy losses?
No.
Then how do you know how much error it is? And how can we just say that the error is from energy loss?
I think our theory calculates, as you can see, the majority of the force, except the interior force of the water between the water and the rocket ship. So the possible answer for our error maybe is the energy loss of the.
Yeah, okay, so I suggest that maybe you should calculate how much error is between your experiment and theory data. And then you can know that if the error comes from energy loss, because you can just look at your experiment theory data and say that you think it is because of energy loss. Do you agree? Okay. Then next, I want to talk about your second experiment. Can you please turn to page 12 and page 13? Yes, so in this experiment, you change the water bottle size. Is that correct?
Yes.
So specifically, like, do you have a value of the size?
The size.
Like, what different size of bottle did you change?
Oh. This one is the 7,500. That's 750 milliliters. And the next one is 2,000 milliliters.
So you only did these two sizes. Yeah, okay, so first I want to talk about why you change the bottle size, because I think that if you change the bottle size, you will change the initial air volume, and according to your study, I think that it is at the value expansion rate.
Yes.
So the air volume will affect the result. Is that correct?
The air volume.
Initial air
Yes.
volume. Yes, and also if you change the size of the bottle, will it change the mass of the bottle?
It's like.
So you think that the change in mass can be neglected?
Yes.
Then how can you show that it can be neglected? Do you have a value of how to calculate that?
Because as I remember, the volume, the mass of the rocket versus the mass of the water is very, like there's a very huge difference. So I don't think the mass of the rocket will really affect that much.
Yeah, but you didn't calculate the value to show that it can be neglected. So I think that maybe you should, like before you show that the mass of the bottle can be neglected, you should calculate and show the data that it is very different, so it can be neglected. And also, if you change the bottle size, this means that you're changing two different things. One is the mass and one is the initial air volume. Then how do you know that which one is the main effect on the result?
Sorry.
Like if you change the bottle size and then, like do you agree that if you change the bottle size, you are changing both the mass of the bottle and the initial air volume?
The mass. I don't agree with the mass of the mass.
Yeah, but you didn't show that it can be neglected from numbers, because I don't know how.
So okay, so for the big, for the 200 milliliters, both the mass of the rocket, I think is around maybe 50 is about 70 grams. So I don't think that affects that much to the whole experiment.
Yeah. Okay. So my suggestion is that before doing your experiment, you have to show that maybe from your theory equation or from your experiment results that changing the bottle size doesn't change the mass of bottle to show that.
So I should.
Yeah, because if you didn't show this, I think that both of the initial volume size and the mass will affect this. So yeah, I think that you should do another experiment or calculate from equation to show you that the mass doesn't affect molecular frequency. Yes. And I want to talk about, I still want to talk about the error of your experiments because you didn't add an error bar, and I don't know how much error is in your experiment. So,
What is the error that you're trying to discuss?
So in the first experiment, you compared your experiment data to your theoretical data, right?
Yes.
Yes. So I want to know how much the error is, because the experiment data is different from your theory. So you can calculate the error from this, right?
Approximately 10%. Like as I mentioned, the larger the rocket, the more error will be caused because of the volume of the rocket. And for the smaller rocket, it only shows like a little error in our prediction rather than our experiment.
So this is only a little bit of error. This is small error.
Yes.
But here, this number is 3.2 something. This is 6 something.
Yes.
So I would say that error.
This is what I mentioned because the larger the mass, the water in the rocket volumes more, causing more error in the track.
Yeah, but this is a smaller mass, right?
Smaller.
750 millimeters.
This is the how can I put it? It is big compared to the size of the rocket. Do you understand?
Wait, so this one is so the 750 is the size of the rocket.
Yes. The total volume.
The total volume of the rocket. So this is not the volume of water.
Yes.
Okay. Yeah, but I still think that 50% is too much to say that it's only caused by energy loss. How can you prove that?
I think the consistent results across varying data and rocket sizes supports our theoretical data.
Yeah, okay, so I suggest that maybe even though if you don't know how much energy loss, you cannot calculate it. I think that you can add a coefficient of into your theory equation, and then you can try to change the energy loss. So you can try to change the coefficient and see what is the coefficient of energy loss, and then try to prove that it is caused by energy loss. Okay, this is a conclusion for the discussion between the referrer and opponent. So first, I talked about the graph. They shouldn't connect 2 points between the experiment data because they don't know the actual value between the 2 points and they didn't do experiments. And also, they cannot only do one time, do the experiment one time and then they didn't add an error bar and didn't show any error. And I think that they need to add an error bar and do the experiment more times. And for the comparison between their theoretical data and experiment data, there are very obvious deviations between them. And I think that they shouldn't just say that it's due to energy loss because they didn't calculate a value to show that it is because of energy loss. And yeah, so they should have done the calculation of the error and show that how much error it is and how much energy loss it will cause. And they also need to show that the mass will not affect the experiment from their calculation. Thank you.
So my first question is directed at the reporter. So in your experimental setup, I see that you use a bicycle pump to pump the water bottle. So how do you control the pressure?
We measure the pressure by the.
How do you control the pressure?
Control.
Yes.
I think we did record the pressure during the launch.
Okay, thank you. So the next question is directed at both the opponent and the reporter. So what do you define as the lift off of the entire experiment?
Is when from the rocket launches to fuel rundown.
Okay, then what do you think?
I think the lift off is from the rocket launches and the motion of from the rocket launches to its maximum velocity.
Okay. So do you acknowledge that throughout the entire experiment, the mass of the entire water bottle rocket is affected through the function of time? So you should discussed in your theory. Like, I assume that it's accounted for mg for gravity and ma for mass. So what do you think it would change if you accounted for the change of mass?
Change of mass.
Yes, because
If the mass here calculated the initial thrust,
but
water provided.
throughout the entire experiment, the mass changes throughout with time. As time accumulates, mass changes. What do you think?
I'm sorry.
They did consider the change of mass below this equation below.
Yeah. Okay.
And I think that the mass of the water will decrease over time because water is coming out.
Okay. So my next question is here. So what do you think? How does the fin affect the entire experiment?
The fin.
Yes. How do you think it affects the experiment?
So for the mass, I don't think it had that much.
As for the mass, how about for the air resistance?
Air resistance. The fin. The fin, as you can see, the fin is inside the water bottle, so it didn't like.
It's inside the water bottle.
The air is like the water bottle width is like this.
Okay.
The air is.
How do you think? How do you think the fin will
I
affect
think
it?
that adding the thing will cause a larger surface area, and then the air drag force will be larger.
Okay. Go to your slide about the formula, the overall formula. I see that there's a drag coefficient there. So how do you account for the drag? How do you calculate the drag coefficient of the rocket?
The drag coefficient is about I think 0.1 to 0.3.
Did you do an experiment? Because it's a pretty big range, 0.2. So have you done an experiment on how you calculated the drag coefficient?
No.
Okay.
I think the air drag coefficient should be. It depends on the shape of the bottle, and they should do it in the experiment.
Okay, thank you. Honorable worthy opponents and fellow physics debaters. This is a review from Team GGWP reviewing the topic water bottle rocket. To start with the common statement, the water bottle flies up into the air with partially filled with water, and then we're gonna the reporter and opponent discusses about the acceleration. And this is a phenomenon. The theory that the reporter uses are the thrust minus drag versus minus gravity, and then some of the theories used are Bernoulli's equation and adiabatic expansion. And for the experiment, the reporter uses a slow motion camera, and the variables that the reporter changes are water amount and changes the volume, and then comparing the two different bottles that they made the experiment on. Let's start with the pros and cons. For the reporter, you need to have the pros are clear derivation of the equation on page both 8 and 9, and then profound consideration of possible deviations on page 13. However, there are still some cons considering the definition of lift-off, air pump, how to control the much air amount, and then how the notations need to be more defined in these pages. As for the opponent, the pros are profound consideration of error in experiment, and then you consider a lot of factors that would result in the error, which is a really good discussion. And then for the cons, you lack consideration of other possible factors, and you mainly focus on trying to discuss the error rate with the reporter, which they clearly did not elaborate on. So for the discussion, you first asked about how, the opponent asked about how linear data affects, why is it linear data, and the reporter says that it reaches intermediate value in the middle. And the next one is about error bar, and the reporter stated many times that they only did the experiment once. The next one, the opponent asks, because of these error bars, the theory must be wrong. And then the reporter says something about their mistype in their PowerPoint. Next one is about what bottle the reporter uses, and the reporter responds with only both 2 bottles. I asked about how to control the pressure, and the reporter says he did record the pressure, which is not a very clear definition. And I asked both the reporter and the opponent about the changes of mass, which will affect the overall formula, and the opponent response is they then consider the change of mass, water will decrease over time. The last 2 questions are the fins, how will the fins affect, and the reporter says it's inside the water bottle, and the opponent says adding the fin will result in larger drag force. And drag coefficient, the reporter didn't do it, and the opponent said they should do it. As for the missing points, you should consider fins into your equations and how it affects the overall formula and the drag coefficients. And as I stated before, the CD is a very important measurement throughout your experiment, and you should measure it precisely and not giving me an unclear example. And the leakage of delta M, as I asked in the overall cross, and then the control of pressure, which definitely needs to be revision because you changed the volume of the water. However, you did not control the precise amount of pressure put into the rotor bottle. Next, the opponent asks about the error, which I completely agree, and the reporter should definitely improve on that. And for more questions, I feel like the reason why you should choose adiabatic equation can be clarified on because it's a very precise calculations that needs to that needs to be accounted for the ideal gas equations and other factors, which you will need to clarify. And then lastly, it's about 2D and 1D motion. You did say a lot of modeling, you didn't really clarify on it's 2D or 1D modeling.
For concluding remark, we use using light and condensing conspiration to get the motion within the rock. The optimal water volume is an intermediate volume around 10 to 15% of the total rocket volume, producing the maximum acceleration, which both insufficient and excessive water will reduce the acceleration. The acceleration will according to the time. The larger rockets can sustain thrust for a longer duration, and larger rockets oscillate more during the data analysis because of the error of the tracker, and the experimental data align with the trend of the experimental and not align with the theoretical predictions. They asked about where does the opponent asked about where the experiment error, the energy loss and the bottle cause it. As I mentioned, the opponent said that we should try to see the impact of the loss, and we agree. But to try to fix this theory and have the problem stated what parameters affects the acceleration, and the trend fits the theory. So we think the experiment fit the theory. The change of the bottle size and mass. The change of the bottle size to mass is small because, as I mentioned, both are 70 to 75 grams, less than 5 grams of change, compared to the change of the water, which is 100 to 500 grams. The air drag force coefficient should be measured. We think the air resistance is small compared to the other terms in the equation, so it is not important.
Okay? Goodbye. Okay. So, questions from the floor?
fit his theoretical model?
I think that he did consider all the factors that would affect the acceleration in the zero model, but their experiment data shows that it doesn't fit the zero model. So I think that maybe it's some considered error in the experiment.
I just asked, do you believe his theoretical model?
Yes, but the experiment actually was wrong.
I guess theoretical model, but there's still some errors considering the fact that they didn't even consider it. My question is very easy. Okay, then can you explain following this theoretical model if there's no water or full of the water in the rocket? The question statement says that it needs to be partially filled with water. I mean, from the theory, how do you explain?
Yeah, so from this theory, if there's no water, of course, there will be no acceleration.
Why? How can I say?
Because the WEX over there, they said is the velocity of water. So if there's no water, there will be no velocity of water. Then there will be no acceleration.
If there's no exit velocity of the water, there's no force. If there's no, because W squared is the exiting velocity of the water. If there's no water, there's no exiting velocity.
I agree with this. Because if there's no exiting velocity,
But I also ask the opposite. If there's a flow of the water, then
sorry.
I also ask the opposite. If there's a flow of water,
Full. If the bottle is full of water, it will not launch out.
okay, you need to explain it from your theory.
Because there's no pressurized air.
The pressure needs to push the air down in order for it to generate an upward velocity, acceleration.
If it is full of water, there will be no air inside, then there will be no pressure to push the water out.
How many free-form can you do? First one, this formula use how many free-form?
Oh, parameters?
And free-form.
Oh.
Should be one.
The mass of the water and the volume of the compressor.
So you can control how you can change the numbers from the experiment. Let's say, for example,
C, or the constant.
that's
Research.
You need to measure with you can measure the terminal velocity of the water bottle by dropping it from upward to downwards, and you can use the drag. And therefore the drag will be equal to mg, and you can calculate the drag coefficient using terminal velocity and drag.
you can get this value from the experiment.
Yeah, you can do it.
I agree with the reviewer. I think that it can be measured by doing experiments of terminal velocity, and also the coefficient of drag force will depend on the shape of the bottle. So I think that the reporter should do some experiments to measure the coefficient.
I have a question for the reporter. Could you explain in detail how you obtain your theoretical prediction? For example, how
We
do you
use
get-
code and the parameters. We type in the parameters of our rocket. And as I mentioned, the
No. Just tell me how do you get, for example, VA or T? How do you get that? How do you get that?
That's it.
So, okay, so just answer me. How do you explain in more detail how do you obtain your VLT? Yeah, just the previous page. Yes. Okay, for example, I would like to obtain your VLT. How do you get that?
We use Bernoulli's equation
Okay.
and array expansion.
And we will have initial value for what?
Initial value of the compressed air.
Anything that is required to obtain the theoretical data.
We have the area of the exit the nozzle and the initial value of the air, compressed air.
So how about the adiabatic index? Gamma.
This?
Yeah.
Yes.
You measure it?
1.1. No.
You didn't measure it.
Yes.
So that's you taking from paper or what? Okay. So let's show the marks on the report. 3, 6, 6, 4, and 5. For the opponents, 7, 6, 6, 6, and 7. For the reviewer, 8, 6, 8, 5, 8. Okay, so that concludes this stage of 5.